Ladies and gentlemen, mesdames et messieurs, meine Damen, meine Herren, it's a great pleasure to welcome you on our Wednesday afternoon webinar about green hydrogen, the dawn of the hydrogen economy, recent developments and activities. Like every Wednesday evening at 7 p.m., it's a great pleasure for me to welcome you all on behalf of the, let's say, Green Hydrogen Society in Tunisia, about the GIZ in Tunisia, about the University in Karthago in Tunisia, on the German side, on the Hamburger Bezirksverein from the VDI, as well as Hamburg University of Technology and the Energy Research Association here in Hamburg. It's a great pleasure for me to see you again. And still, we are in the area of transport and storage of hydrogen. And on this background, we had last week discussion or some presentations about, let's say, hydrogen and salt, where we tackled a little bit the questions below ground and above ground, where we looked a little bit deep into technology and into geology. And then we had a discussion about hydrogen storage in metal hydrates. This week, ladies and gentlemen, we will, let's say, focus on developments in hydrogen storage. And therefore, it's my great pleasure first to introduce Claudio Pistida. He is a scientist in the Herion Research Center and Institute for Hydrogen Technology. I hope I make no mistake. Here close to Hamburg in Geesthacht. And he will give us a presentation about the basics of a storage of hydrogen in chemical media. So therefore, he gives the basic, the ground and the base level of what is technically or chemically possible in storage. And then, ladies and gentlemen, we will have afterwards a presentation as already announced in the field of chemical storage, hydrogen storage in salt systems. This will be done by Volkan Turan from Apex Group in Germany. And then we will also again tackle the question, because this is the most important, this is the, let's say, the most important point, hydrogen storage in salt caverns by Daniel Mercer from Store Energy in Germany. This is what you can expect tonight. And unfortunately, I have, let's say, to pass over the moderation then, let's say, in roughly half an hour to Fabian Karels. He will do it because I will most likely not be available, because then I have to be offline, because otherwise I have no chance to come back to Hamburg. So from that point of view, first of all, thank you very much to all the presenters, and thank you very much also to the institutions that they are willing to support us. And now I give the word to Claudio, giving us an overview about the chemical hydrogen storage options. Claudio, the floor is yours, and we are interested in your speech. Please go ahead.
Thank you, Martin, for the kind introduction, and thank you also for giving the opportunity to present here today. So now I'm going to share my screen, and I hope you can see it. Fine, good. So as Martin said, my topic today is hydrogen storage in chemical media. My presentation, it will be rather general, but it will be the base for the discussion today. Now, so let's move. So a short outline of the presentation. So we will speak about why we are trying to store hydrogen, what is in the background. Then we will see what are the properties of hydrogen as an energy carrier. And we will see that we can store hydrogen in liquid media, but also in solid chemical media. Now, we are heading toward an hydrogen economy, and that it's clear. And we know since long that hydrogen could be a really nice, really friendly energy vector, but energy vector for renewable energy. So what we want to do with this hydrogen in our hydrogen economy. So if we look here at the picture on the right side of the screen, you can see that we want to produce hydrogen in a sustainable manner. So, for example, through electricity produced from renewable energy sources, then we do water splitting, and then we have to vehicle this hydrogen to several different sectors of our economy. And the fact that there are several different sectors calls for solutions that are flexible, solutions that are different but efficient at the same time. Now, hydrogen, if we look at the periodic table of the element, is located in the upper left corner. So it's the simplest of the element in the periodic table. Now, hydrogen, we are looking for hydrogen as an energy factor for a simple factor. If we look at this graph here, where mass energy density of several different compounds is shown, you will see that hydrogen has the highest mass energy density compared with some of the most common fossil fuels. However, this picture is reversed where we look at the volumetric energy density. Before we were looking at the gravimetric one. So at the volumetric energy density, what we can see is that hydrogen has a rather low energy density, even if we try to compress or liquefy to improve this value. Fine, these are general properties of hydrogen. And now we have to find a way to store or to bring around, to transport this hydrogen once that has been produced. Now, there are several different approaches that can be summarized in two categories: physical approaches to store hydrogen or chemical approaches. On the physical side point of view, we can try to, as we said before, to compress gas, we can try to liquefy, we can try to compress at cryogenic temperature, or we can try to store this hydrogen on large area surface material like MOFs or carbon-based material. Now, these are physical methods where hydrogen is stored in its molecular form. However, we can also try to break this molecule of hydrogen and to try to store hydrogen, chemically bonding it in atomic form to a compound. So we can have carriers such as the liquid organic carrier, example, benzene, toluene, or circular carriers like ammonia or methanol, or solid hydrides, where hydrogen is bonded to a metal or in a complex metal hydride. Now, for today, we are interested in the chemical media, so we are looking to this side of the picture. Now, let's start here. We said that there are several different possibilities to store hydrogen. These two graphs here give us an idea of how, for example, this graph here on the left-hand side, the volumetric hydrogen storage density is for metal hydride, liquid organic carriers, ammonia, complex hydride, in comparison to the hydrogen storage through physical methods. So we're speaking about liquid hydrogen and gaseous hydrogen. You can see that the possibility to store in chemical media hydrogen give us some opportunity to increase the volumetric hydrogen storage density. And if you look at this graph here, you can see that this higher volumetric energy hydrogen density is achieved at condition of pressure that are relatively mild. In fact, if you want to achieve an high volumetric hydrogen density by compressing the gas, you have to go to extreme pressure, or like in the case of liquefied hydrogen, you have to go at cryogenic temperature, so extremely low temperature, minus 253 degrees C. Good, so that was a general picture of how the storing of hydrogen through chemical media may lead to an improvement of the volumetric hydrogen storage density. And now let's move to the liquid organic hydrogen carriers. Now, liquid organic hydrogen carriers are organic compounds that can absorb and release hydrogen through chemical reaction. Now, so that is quite nice. So what does it mean? It means that these compounds have an unsaturated C-C bond, double bond or triple bonds, where hydrogen can insert itself. This kind of material were studied since 1975, 1980, so are quite recent. Now, here you can see an example of compound that may be considered for such an approach to transport hydrogen. So you can see we go from extremely simple molecule to more sophisticated, more complex molecules. Now, how does it work, this insertion of hydrogen in this unsaturated bond? So you can see here an example of toluene, where we add hydrogen. And of course, the reaction doesn't occur spontaneously, although thermodynamically it should be favored. But in the presence of a catalyst at high pressure and temperature, what happens is that the hydrogen enters the bonds, and we move from toluene to methyl cyclohexane. And then here, although this molecule is stable at ambient condition, if we want to retrieve the hydrogen, to take hydrogen back, what we do, we use again a catalyst, and we work at low hydrogen pressure, practically ambient condition, but quite high temperatures. And then what we obtain is that we move back to toluene. Now, here is an example of several different compounds that can be used for storing the hydrogen. So some of them were shown previously in this graph here. Now, what you see here is that you can see how many molecules of hydrogen these compounds can take in. And you can see that this reaction theoretically is spontaneous, should be spontaneous, because it's largely exothermic. However, we have to say that without the presence of a catalyst and appropriate temperature condition, this reaction doesn't take place or occur through sluggish kinetics. Here, you can see that the hydrogen storage capacity, expressed as a gravimetric value, it goes from 4.3 to something like 7 weight%. This is not bad, but we have to keep in mind that this high reaction enthalpy will be translated later in high stability, and therefore the use of relatively high temperature, and then to an heat management of the storage system that is quite complicated. Now, what we can say about the liquid organic carrier? So we can say that the hydrogenation, so it's exothermic. However, we need the condition of 200 to 420 degrees C to make it occur with kinetics that are acceptable under a pressure of hydrogen that is between 20 and 50 bar. It's not extremely high, but it's quite high, this pressure anyway. Good. The good thing is that the hydrogen, once it's loaded, and once the liquid organic carrier is hydrogenated, is stable under ambient condition, and you can keep it the hydrogen bonded into the molecule for a really long period without anything happening. There is not a loss of hydrogen. So the handling of this material is quite simple compared to gaseous or liquid hydrogen. Not high pressure or extremely low temperature are necessary. In particular, these liquid organic carriers are behaving like some of the most common fossil fuel, no? Like diesel, gasoline. So it's easy to transport, easy to pump. So not extreme care is necessary for handling them. On the other side, we say that for hydrogenating, we have to provide high temperature and high hydrogen pressure. For the hydrogenating, we have to achieve, again, high temperature, 200 to 450 degrees C, but the pressure, it's nearly ambient pressure. Good. What we can say more is that due to side reaction, once you cycle, no, you charge hydrogen, you discharge, you charge, you discharge, some of the capacity of this carrier is lost. And after a while, the replacement of them or of the catalyst utilized is necessary. Now, ammonia. So ammonia is something that we are more familiar with because it's used already abundantly in our industry. No, we know, for example, that ammonia stinks terribly. What we don't know is that ammonia is the simplest hydride of nitrogen. And we know also that at ambient condition is a gas, but when you increase the pressure to 9.2 bar, it turns into a liquid. And once it's liquid, it contains a large amount of hydrogen. So we are speaking about 17.6% in mass. And thanks to the fact that it's relatively dense liquid, we have a volumetric hydrogen density that is 45% higher than the density of liquid hydrogen. What does it mean? If you look at this table here that shows the volumetric energy density for several different fuels, you will see that ammonia in the liquid state, in particular minus 35 degrees C, has a volumetric energy density that is higher than hydrogen in the liquid state. Just that one is at minus 253, the other is at minus 35, and already at ambient condition, in the liquid state, the volumetric energy density of ammonia is higher than liquid hydrogen. Good. So once we have hydrogen, once we stored hydrogen, green hydrogen into ammonia, what can we do? Well, we can take this hydrogen, this ammonia, and to burn into an internal combustion engine. No carbon dioxide is produced, most likely NOx. Fine, we have to check that. Or we can use this ammonia and then to crack it to produce high purity hydrogen and then to feed the fuel cell. No, these are the two possibilities. Fine, we say that we can crack ammonia and to feed a fuel cell. If you're speaking about a PM fuel cell, we have to pay extreme attention to the purity of the flow of hydrogen, also because few ppm of ammonia will damage badly our fuel cell. So the cracking and the purification of the stream of obtained hydrogen is a crucial aspect of this process. Now, this is one of the smallest bottle of ammonia liquid that you can find on the market. What we can say is that the production of ammonia, it's already something that is happening at the industrial scale, because it's used as a fertilizer, it's used in the as a refrigerant, it's used in the pharmaceutical industry. So it's something that it's available on the market in large quantities. Now, the handling of liquid ammonia, it's for industrial people with industrial background, it's relatively simple. No, for normal people, it's not, because it's a toxic gas. Therefore, its application in urban area, it's something that is a little bit constrained for the future. Now, what we can say is that given the high hydrogen, the high volumetric energy density of ammonia, it's a good candidate for seasonal storage of energy, no? And therefore has the potential to be utilized immediately for energy storage. And actually, also the possibility to produce ammonia where renewable energy sources are available and then to ship through long distance is something that plays in favor of the utilization of ammonia as an energy vector or as a hydrogen vector for the future. Now, metal hydrides. So there was already a presentation the last week about the metal hydrides. Now I will be quite brief on it. So what can we say? We know that metal and metalloids have a strong affinity for hydrogen. Now, this affinity leads to the formation of metal hydride species. No, you can see here the reaction that is simplified. So metal or metalloid react with hydrogen to form a metal hydride, and this reaction is again largely exothermic, and some heat has to be released. But what are the elements that can form a metal hydride, MH bond? So as you can see, it's a large part of the element reported in the periodic table. Now, we have, I spoke about metal hydride, but there are several different kinds of metal hydride. Simple metal hydride, like the palladium hydride that was discovered by Graham in 1969, really long ago. But we have also more complex metal hydride, like sodium boron hydride, lithium boron hydride, alanides. So this compound, they're also really old, but just in the 1950s, 60 were started to be considered as a potential hydrogen carriers. Before not, they were just considered as a laboratory curiosity in the chemical labs. Then, since the 2000s, a new approach has been developed, because complex metal hydride have a really important feature, property. So they can store large quantity of hydrogen, but are rarely fully reversible. And that is an issue, because what we want is to create a reversible storage system. So what was developed in several different centers, among which our center are the so-called reactive hydride composite, where different hydride species, of which one is the complex metal hydride, are combined together to form a system that has still high hydrogen storage capacity, but it's fully reversible and has thermodynamic stability that is lower than that of the single compounds. So this is a great advantage, and this is something that is continuously developed. But as you heard, this approach was discovered or was brought to practice in the 2000s. So it's a relatively young approach compared with, for example, the Haber-Bosch that we saw for the ammonia, that it's 100-year-old. Now, why to store hydrogen in solid state in the form of metal hydride? Well, here you can see clearly in this graph here. Now, let's assume that we want to store 6 kilograms of ammonia. That is more or less what is needed in our fuel cell electric vehicle to make 600 kilometers. So if we store hydrogen in compressed gas form at 350 or 700 bar, we will need a tank that is 230 or 142 liters, respectively. Okay, that's quite a big tank. If we will liquefy our hydrogen, the tank is shrunk to only 84 liters. But if you use a metal hydride, this tank can get as small as 40 liters, perhaps a little bit more, but extremely small. So you have your hydrogen confined in something that is really tiny compared with the storage in compressed form or liquefied form. So this is one of the main advantages of using metal hydride. Moreover, you have thermodynamic properties that are really broad because the chemistry of metal hydride is really broad. So different conditions, different application. So a really huge flexibility of using this metal hydride in different applications. Now, what you can say about metal hydride? Metal hydride-based material can reversibly absorb hydrogen over a broad range of temperature and hydrogen pressure. The loaded metal hydride can be stored at ambient temperature under an inert atmosphere for long period without any energy losses. This is like in the liquid organic carrier or like in ammonia. So the hydrogen containing the hydride material can be released as at extremely high purity by varying only the container, the tank, temperature or pressure. CO10 is super pure, so no problem of coupling with a fuel cell, no problem of poisoning the fuel cell. Now, given their high volumetric energy density, metal hydride-based hydrogen storage systems are leading candidates to manage variation in electricity demand or short-term backups for intermittent generation from renewable. So this is something that is extremely important. So now I reached the end of my presentation and we have to conclude. So what we want to do is to use a renewable energy source to produce hydrogen. And then we have to find a chemical media, so a chemical we can, to store this hydrogen and to transport this hydrogen. So we saw several different possibilities, and there is not a winner. No, there is not a winner, that is clear. But chemical hydrogen storage can be carried out using several different compounds, and these compounds have different properties that allow us taking the decarbonization of several different industrial sectors. But we're speaking about industrial sector that cannot be directly electrified. That has to be kept in mind. Now, among them, there was not a winner, but certainly the ammonia is a strong candidate because it's already industrially available in large scale. So, and there is a really huge know-how behind how to synthesize ammonia, how to crack ammonia. Of course, the possibility to use liquid organic carrier or metal hydride give us an additional degree of flexibility that is what we need to achieve a mature hydrogen economy. Moreover, what we can say is that beside designing high quality, high performance material, what we need is support in international collaboration, support from politicians, for organizations, and we need to bring this solution to the scale that is required to make a real impact. Now, I would like to thank you all for your kind attention, and I'm looking forward to your questions.
Yeah, Claudio, thank you very, very much for this very interesting presentation. And thank you very much also for, let's say, developing this presentation very sharp and very target oriented to what we're discussing, let's say, what we discussed last week and what we discussed this week. So thank you very much for this very nice overview. We will now continue with our presentation and we'll come back afterwards, after we have this presentation, with a, let's say, short roundtable discussion where the questions which might pop up in the chat, which then are tackled. And from that point of view, thank you very much for your presentation and thank you very much for taking time. And now it's my great pleasure to move over to Volkan Turan. He is from the Apex Group, and he will give us a presentation about one specific option to store hydrogen in salt, if I understood it right. So please correct me if I'm wrong. With this, I would like then to pass over the moderation for the next time to Fabian Karls, because as I said, I have to, let's say, leave now, and I will be back, of course, next week. But I'm very confident that Fabian can do the job even better than I can do it. So, Volkan, the floor is yours, and we are listening to your presentation. Please go ahead. Thank you very much.
Thank you so much, Martin. First of all, I as well would like to thank you very much for the opportunity to be part of this hydrogen webinar. I have to admit I could not have had the opportunity to be part within the last, or to participate within the last meetings or last presentations. So I wasn't 100% sure how deep I should go into the chemistry, but I'm quite glad that Claudio did this perfect and awesome introduction. And I am as well super happy that I think that I can still add a lot to Claudio's chemical storage systems, and maybe even add something so that Claudio can in the future or near future add another chemical storage system to his chemical presentation overview. So first of all, once again, my name is Volkan Turan. I'm a process engineer currently working at Apex. And I would shortly as well use this moment to introduce the company as well for those who don't know us already. Basically, the Apex Group is currently based on two major pillars, which is on the left side that you can see here, the project business, and on the right side, the hydrogen storage business, where I am as well working on. But I would like to as well introduce shortly the projects. On the left side, project business means the EPC, EPCM that we do all from engineering to procurement until construction, but as well management. And we even own our own plants that we operate by ourselves as well, which is quite unique. And on the right side, we have the storage, which is from tank development for high pressure tank that Claudio as well was talking about already, to trailer solutions up to chemical storage as well, which I'm going to go or dig a little bit deeper a little bit later. So first of all, what the Apex Group exactly does is that we have identified 4 major areas in particular where we see the greatest potential for decarbonization. And these areas are the industry, energy, mobility, and buildings. And Claudio as well, he did so many great things. He said that I actually was supposed to tell you as well. So as he said already, industry, I think, is one of the major aspects where you have to decarbonize quickly. And this is our, let's say, profound know-how, what we have already in the industry and the energy sector, and currently building further into this mobility and building part as well. But what we see on the left, this is what we currently have the most profound know-how so far. And therefore, I also wanted to bring, for example, 2 short examples on what we are currently building or what is in construction already, which is, for example, the perfect example for steel or for industry application, which is the CO2 neutral steel production. So we partnered up with ArcelorMittal and built this let's say electrolyzer in order to produce green steel. And I brought you a few key indication parameters, let's call it that, at the bottom. But for me, I think always the most important one, or the most interesting and motivated one as well, is the CO2 reduction that here it says is 21,000 tons per year that we can save in order, or just with this plant, which is one of the few that we're currently in production already. Another one, which we're quite proud of, is the so-called H2 Eero. because this is actually a European flagship project, which means that we are part of the important project of common European interest, the so-called IPCEI projects, where we are part of a consortium which aims to develop a hydrogen exclusive gas network in northern Germany, where we will provide a large amount of hydrogen that is going to be fed into the grid directly. And here as well, again, there are parameters on the bottom left, where is the CO2 reduction, 90,000 tons per year, which again, I think is quite promising and motivating for all the work that we are currently doing at Apex. So you have seen the picture of this H2ERO project. I just wanted to share you this picture of the headquarters in Rostock-Lage. So we are in Germany as well, in the Baltic Sea area. And this is our headquarters. And just behind the U, what you see on the neutral, there's the part of the H2ERO project that I was just showing. Currently as well, we are Europe's first CO2 neutral industrial park, which means and luckily or fortunately, it's being expanded more and more with time. So we have already other companies partnering up and using the energy, the hydrogen and the heat that we're producing on this industrial park. So yeah, we're quite proud about that as well. And what I said is what our quite unique thing is, you see this here on the bottom left, quite small, is that we operate our very own Apex plant, which is, I think, one of our key strengths, that we have been operating our own hydrogen power plant directly on site for quite a long time now, and have thus been able to collect real-time data before many other market competitors who are projecting hydrogen plants, and are still able to learn from our own operation today still, and learn from the data that we're generating permanently 24/7. And this leads us there that we have already even, as I said, some customers. I think one of the most favorite one, I brought this here one as well, is the Amazon, because Amazon has quite close to us a logistics center that we supply with hydrogen as well currently. And we even have the first right to pitch for all German locations to supply them as well with hydrogen in the future. That is everything I wanted to say to introduce the company. So I hope I got some, or I woke some interest in you in investigating a little bit further on our website probably. But I would already now jump into the topic of storage hydrogen. But before I go into the chemistry, I would at the very beginning as well, just like a brief overview as well on that topic. What Apex is doing, because we're not focusing only on chemical storage, but on several storage technologies. You see here 3 different pictures, like the stationary compressed gas storage on the very left. You see a portable compressed gas storage and fuel storage system, so an entire container where the several tanks are stacked into one container in order to increase the amount of hydrogen that you can store in one of these systems. And on the right side, the chemical storage, I have to apologize, like this is not the actual picture how it looks inside the containers, but I think you can understand from, as it is our IP at Apex and what I'm going to show you now, that we don't provide 100% insight to what's inside our containers. So this is from the storage side. And I am, as a process engineer, currently working especially on the very right one, on the chemical storage, which I would like to show you now with my further slides. But having said all that, I just want to clarify one more thing, because sometimes we get asked whether the different technologies, the compressed gas storage or the chemical storage, why we focus on both of them, and whether they don't or not opposing technologies. But luckily, as Claudio said already, that there's currently no winner so far in the hydrogen storage, let's call it competition or race. And we actually don't see them as opposing technologies, none of them actually, but rather as complementary, because we think that for each project, or let's say for each application, there can be several products or several technologies that have their pros and cons and advantages for the specific application you would like to use it for. And that's why we think they're all actually complementary. And said that, I would like to show this slide, which I think is actually quite important, because sometimes I get the impression that whenever people are talking about hydrogen storage or hydrogen technology, the only thing they're only focusing is, unfortunately, always the energy density. And it's the only criterion considered in the discussions. But in fact, there are countless of parameters that should be included in such considerations. And we think at Apex that the energy transition actually means not winning a competition, but rather diversification of technologies. So that means that every technology may have their part of the entire share, or let's say a share of the entire market, as I said, because every technology has their advantages. I just brought here a few of these parameters, which I think are quite interesting or important as well. So besides the energy density, Claudio was talking already about the gravimetric and volumetric energy density, but we think that there's way more, especially, for example, the carrier material, especially if you're talking about chemical storage. You have to check the availability of the carrier material, you have to check the price. How about the handling? Is it flammable? What's the safe aggregation? Can you integrate it in current infrastructure already? How is the toxicity, the pollution? Do we have any effect of environmental, or let's say ecosystem, aquatic systems? Is there any hazardous CO2 impact? And how about the efficiency? So I think these are all different parameters that we really have to focus, and not only on one, the energy density. And this is where I would like to introduce our new system, which focuses, I think, on all of them. I have to admit that it is not one of the most energy dense ones. We just saw the different graphics from Claudio, but still we think that all of the other advantages that we provide with our system, that we still can have, as I said, a fraction of the market or the share as well. And the cool thing about our chemical storage technology is actually that we have a pressure storage hydrogen in liquid or in solid form, which means either in a salt or in a solution. So what I want to highlight here is that although I'm talking about salts, we have to keep in mind that I am not talking about storing hydrogen in a salt cavern. So what we're doing is, I'm going to show this on the next slide. What we're doing is we're storing hydrogen chemically, as we've seen it on the LOHC just a few minutes ago, as a reversible battery. And we do it with a salt system, which means like we have a salt where we add chemically the hydrogen to it. And that makes it completely non-toxic, non-corrosive, non-flammable, and completely safe. It is integrated into infrastructure quite easily. As I said, we even have the chance to have it as a saline solution, as a brine, which we can pump through pipes, for example. And through all these advantages, I think that we can achieve quite a high acceptance due to all this easy handling, and especially due to the lack of the necessary safety equipment, for example, or safety measures. Another cool thing is that our system is quite efficient in storage and release of the hydrogen. I'm going to show that, well, yeah, to say the next slide. And dependent on the form we use, whether it's either liquid or solid, we can achieve different energy densities. So how it works, I brought you the principle here. I would like to start on the left side first. And you see there the picture, like the cycle. And as I said, our system actually works exactly like the LOHC that Claudio already mentioned, as some kind of a battery. So we have an empty battery and a loaded battery. The empty battery is a salt, which is known as bicarbonate. And the interesting thing is about bicarbonate, potassium bicarbonate is the salt that we're using. It is quite known, and we actually, there's a lot of people who even use them in their use it in their kitchens. This is in the industry well known since decades. And what we can do is we can now load this bicarbonate, the empty battery, with our hydrogen, and get the hydrogen enriched form, the so-called formate. And the formate is a derivative of the formic acid, but that has nothing to do with the formic acid itself. So it doesn't mean that it's suddenly corrosive or toxic. So it's only the salt which is derived from the formic acid. But this is our enriched form. And as I said, like the entire cycle makes hydrogen suddenly pressureless and safe and non-toxic. On the right side, you see both salts. Please excuse me, I did not have the time to prepare this slide with the two salt vials in English. I actually have them with me. I brought them with me. I don't know whether you can see this. It's written here in English as well. So this is the formate salt, and I actually can open this. Unfortunately, you just have to believe me on this stage that this is not any other suspicious white crystalline salt. But I actually can just stick my hand to it. It's completely pressureless. It's safe. I could actually even eat it. It actually does not have my favorite taste, but it's still, as I show you, there's no safety issues with it at all. On this page, as I said, I didn't know how deep I should go into the chemistry, but I want to mention it because Claudio said that as well in his slides. And I think there's a major or key aspect where we differ from the known LOHC so far, because he said that currently, in order to get the hydrogen out of the battery again, of the currently discussed LOHCs, we need temperatures from 200 to 400 degrees Celsius. And our system actually works as well, as he said, with a catalyst. So it's a catalytic system, but we can do this already even at ambient temperatures, although then kinetics is not that favorable, but we can do this already at around 60 degrees Celsius. And the good thing is that it's not extremely exothermic or endothermic, so we don't need that much of energy in order to run our chemical reactions, which makes them in the end, as I said, very efficient. Another very important aspect is that we don't have any side reactions. As Claudia said, the problem with the LOHC, the longer, or let's say the larger the molecules become, the more side reactions you could have, which are somehow a problem as well and are decreasing the effective energy density. As our molecules, the bicarbonate and formate, are so easy and small, let's call it that way, there's not that many side reactions that actually could possibly happen, which makes our system as well very good to handle, as well from the process side and the chemical side, which makes this a favorable system as well. Yeah, so on the next slide, I was talking already about the two different, let's say, ways to store hydrogen in our salt system, which could be either in the crystalline salt, as I just showed here in this vial as a crystalline salt, but we can, on the other side, or the other hand, just dissolve the same salt into water, have an aqueous solution, a brine. And the advantages of having the opportunity or possibility to have this easy interchangeable state of, I just call it state of aggregation, gives us several advantages and possibilities, and even actually some kind of room to interact in different kind of use cases, which means, for example, dissolved in water. So the salt dissolved in water is, of course, easy to pump. It's liquid, we can pump it. But on the other hand, it decreases in energy efficiency, in density, sorry, not efficiency, but density, because you have to imagine in this very small vial, I didn't bring the numbers on slides, but I can actually tell you, Claudia was talking already as well a lot about energy density. And this small vial, actually, the salt in its crystalline form, has a volumetric energy density, which corresponds to hydrogen, compressed hydrogen, at a pressure of around 800 bars. So all the comparisons that we have seen, the slides before, and that is why I'm very happy about the slides and the presentation, which was awesome from Claudio. I really liked it. Shows that it is not that energy dense as, for example, the ammonia or methanol, or not even liquefied hydrogen, but it's still better than the 700 bars compressed hydrogen. So we think it's still favorable to use such a salt system compared to high pressure hydrogen gas. So that is what I mean. If we have this salt and now start to dissolve it, then of course you can imagine we have way more water and less salt molecules in the same amount, or let's say volume, dissolved in water, which decreases the energy density. But on the other hand, it increases the process efficiency. And that is because the system, or the entire chemical reactions, which are catalytic, work in aqueous phase. That means we pump it through a reactor or through our system and get the hydrogen in or out of it. And due to these, let's call it properties, we figured out that the stationary application for this liquid brine is actually one of the best. And as it is liquid and formate is an organic salt, you could actually call it as well an LOHC. That is why I have here on the left side. And on the right side, if we keep it as a crystal and in a crystalline and solid form, of course, it makes it a little bit harder to handle. So suddenly we cannot pump it anymore. So we have to convey it, or maybe have suction tubes or something similar like that. But what it does is suddenly we have this high energy density that I was just referring to, this 800 bars of hydrogen pressure. But on the other hand, unfortunately, we have this trade-off. We always have this trade-off of high energy density and lower efficiency, or vice versa, because, as I said, the reaction happens in aqueous phase. So if we decide to use the crystal salt in solid form, we have then to crystallize it, which is, of course, another conversion, let's call it conversion step, which then decreases, of course, efficiency again. But with all these properties, especially with the higher energy density, we figured out that in this case, transport of hydrogen is rather the use case. And actually quite interesting. So we have this same salt system, but we could actually either call it LOHC on the left side or SOHC. So it's a solid organic hydrogen carrier. So said all that, I brought you these two use cases, which is either the stationary energy storage or the energy transport. These are the two different use cases where our system is like applicable to. If we check out what are the different possibilities or why we would use them in the two different use cases, is that in the stationary storage, of course, we use them, for example, for the seasonal storage of renewable energy. So you have renewable energy, you have to store it, let's say from summer to winter, for example, and you can make that the seasonal storage. You can even have, sorry, decentral applications for hydrogen. So I think the stationary makes quite a lot of sense. And the other thing that Claudio said already, considering ammonia, for example, as a hydrogen vector, is the global transport of hydrogen, which has this appeal of the aerial connection of supply and demand and the oversea transport of hydrogen carrier. Why is that? I think this is clear to all of us, is that the distribution of hydrogen is actually currently still a problem. I brought you this picture, which is from the International Energy Agency. I don't want to discuss all the numbers on the legend on the right side regarding different colors, but I want to highlight here that we can see clearly from this map that there is areas in the world, these are the red ones, where you can produce green hydrogen way cheaper than you can do it in the countries with the blue color, for example. And on the left side, I wrote that there is the high demand of hydrogen is especially in the industrialized countries. And if we check, like in the majority of industrialized countries, let's say Germany now as an example, or entire Europe, it's not blue, but it's not like a deep red as well. So what we have currently, the problem is that we would have a higher necessity of hydrogen that we can produce ourselves, which means that we have the excess energy in other countries that we have to transport to countries that have a higher demand than production capacities. We see, of course, a huge business model there, but not only from, let's say, the economic or business motivation. I'm still quite a young scientist, so for me, of course, the motivations as well, like saving the world, or at least have like an impact, a positive impact on our CO2 footprint. But we still see like this need or the necessity of the hydrogen transport. And basically what this would look like then, again, just something like this, that we have two different areas. I try to show this with two different rectangles. On the left side, we have the areas with excess energy. On the right side, we have the rectangle with the areas of energy needs. And of course, on the left side, where we have this energy or this like the abundance of energy, we have the renewables. We can use electrolysis, we can produce hydrogen, and then somehow store it into a carrier, get it to an area with energy needs, have some kind of device, or I just call it here release unit. You can again extract the hydrogen from the carrier and then for whatever purpose use the hydrogen. And what we are focusing with our system is now currently this. As I showed you at the very beginning already, Apex has the profound know-how already in the renewable energies and the electrolysis and handling of hydrogen. And currently, for the same system that I just showed you, we are building a pilot plant, say a small demonstration plant, which then shall show in a little bit bigger scale than only the lab scale, the proof of concept that it really works, a storage and release unit, in order to have this possibility as well with our salt system. And you see maybe here as well that we have two vessels. One is going from the storage unit to the release unit, and one is going back. I showed you already our cycle or the battery cycle. What we believe as well is we really like all these cyclic and closed loop systems, and because only through those closed loop systems we really can make sure that we don't have any local CO2 emissions, which of course leads as well in two ships. So one is carrying the loaded carrier to the release unit, and the let's say unloaded salt where we have discharged the hydrogen from already has then to be sent back to the area with excess energy. But this is what we're currently really pushing forward to show that it's possible as well on a bigger scale. And I actually would be very, very happy maybe to, as I said at the very beginning already, to get to this proof of concept that Claudio maybe in the future is then as well going to talk about if he does such overviews again, as well maybe on our formate bicarbonate cycle. So before I end, I as well just mention that we have like a huge network of partners already. So this is not even actual anymore. So this changes like every day. There's going more and more. So it's quite a young and new approach, but we really try to push it in order to really get fast to a good technology, because we really see the necessity currently that we have to make something quickly in order to get to decarbonization or the energy transition that everybody's referring to. And as my last slide, I would like to close this. We have read the name Jules Verne today already, which is a little bit our slogan in the company. Water is the call of the future. This is what we believe. We think we can make a change, can have an impact. And I'm actually, once again, very, very happy that I had the opportunity of being part of this webinar series. And I thank you very much for all the attention. And I'm going to be as well glad to answer your questions at the end of the presentations. Thank you very much.
Yeah, thank you very much, Volkan, for that very interesting insights into that newly innovative approach to store and transport hydrogen. Very interesting. very innovative, and yeah, let's see what's going to happen in the future. Because we are already advanced in times, I don't want to spend any further time here and just pass it over to Daniel Mercer from Store Energy, who will again show us some projects and some information and details about the possibility to store hydrogen in salt caverns. So Daniel, the floor is yours.
Thank you very much, Fabian. Thank you for the opportunity to speak during this webinar and to present our activities in the domain of storing hydrogen in salt, but in a different way. We would store it in salt caverns. So I'll try and give you an overview of why we want to do that and what it would mean. First of all, we'll talk about the company, Storengy, in brief, and why I'm even holding this presentation to you. Storengy is the daughter of a large energy supplier called Engie, that some of you may know, especially those who are in the Francophonic webinar. Storengy basically imports and transports and distributes large amounts of gas, and to do so, it also needs to store it. This was a fact that was enjoying rather comfortable anonymity until around about a year ago, when we were propelled to the front of the scene in the energy world. And everybody can now see how full our storages are. If you're in Germany, you can just go to any newspaper. That's generally on one of the very frontmost pages. So it's a system that allows us to store energy. We store roughly 1/5 of the energy that we need underground. We store it in various technologies that we'll see later. So we consume per year in Europe at large rounds about 5,000 terawatt hours of gas, and we can store rounds about 1,000 of that. Storengy is a company that represents roughly 10% of the market in Europe. We are present mainly in France, in the UK, and in Germany. In Germany, we represent 6 to 8% of the market, and we store our gas mainly in the north of Germany, also a little bit in the south. And we've been filling our storages all the way to Christmas, as everybody else has been doing. And now we are slowly emptying the storages at a rate that is, for the moment, rather comfortable. Storengy in Germany has 150 employees. It stores 1.6 billion cubic meters of gas, and it does so in a very safe manner. So we have a very good, safety record. That's one of the things we do. We are also, of course, looking at the production of biomethane, and also at the idea of storing not just methane underground, but also hydrogen. Why would we want to do that? I suppose the audience is already convinced, but just to give you a little reminder, here's a graphic on the total primary energy consumption in Germany. And the total energy consumption is not just power, which we talk about quite a lot. It's also molecules. Power represents roughly 1/5 of the total energy system. Molecules does the rest. As you can see, we have had in the past, and have still now, on this graphic from 1965 to 2020, roughly 40% of oil in our total primary energy supply. That's for transportation. Coal that used to produce a lot of power, it's still doing that. It's also used in the industry to produce steel, and we still consume quite a large amount of coal. We're still at 15% of our total primary energy supply. Gas, a little bit more than 20%. Gas we use mainly for heat. It can be the heat that you're enjoying in your room right now. It can also be the somewhat higher level of heat that you need, for example, to produce glass, or what you would need in the chemical industry. If you need some steam, steam would be at 250 degrees centigrade and at 25 bar, for example. So very high levels of heat. All in all, we have quite a lot of these energies. If you take nuclear, what's left of it up here, you have roughly 82% of the total primary energy supply today in Germany, which is not renewable. So in the past 30 years from 1990 to 2020, we managed to increase it from roughly 5% to roughly 18%. And according to the laws that we passed and the regulations that we have at the European level, we have 30 years to do the rest. So it's a tall order. It's a big job to do. And the system that we're aiming at is a system that is going to be mainly electrified. It's going to be based on renewable power. And this renewable power has the tendency to be intermittent. So if you were to look out your window right now, you would probably see that the sun's not shining, and you could probably also guess that the wind is not blowing particularly hard. Were you to quantify that, you would see that you have large surpluses in the summer and large deficits in the winter. These surpluses and deficits are sufficient for what we would need. We could build a park of windmills and solar panels to provide all the energy that we need. That's perfectly possible. But we need to take the energy, the surplus energy that we have in the summer, and put it into the winter. That's the overall picture. So that explains here the graphic on the top left. So here we have, say, a theoretical view on a day, and that would be a day in summer, and we would have a very large surplus, and in a day in summer, everything would be fine. For a day in winter, we wouldn't have enough sun energy to provide all the energy in the day, so we would have to take the surplus from the summer and provide it in the winter. So intermittent renewable energies, a form of storage, a grid to provide it to everyone, and that should be fine. What kind of storage is available to us? Here you have a graphic that most of you know. On the horizontal axis, you have energy. Please note this is a logarithmic scale, so every time you move one, you multiply by 10 the amounts of energy. Moving upwards on the vertical, you have time, again a logarithmic scale. And so, of course, first you have things derived from the electronics. Flywheels, they can give you a good voltage control. So if you have an industrial site where you're, for example, producing microchips, you'll probably have something like that to keep your voltage well under control. If you are, for example, a hospital and you can't tolerate that power goes away because you're in the middle of an operation, of course you have batteries, and that will probably get you through a couple of days. Batteries provide also a very good system to control the frequency of the power grid. So we always keep it in a very narrow band around the 50 Hertz level. And we can do that best with batteries. So batteries provide a lot of capacity, but they generally don't tend to provide a lot of energy. Should you want a lot of energy, you have to go towards other systems. You can use mountains. So you have a lake at the top of the mountain and you have water in there and you let it down. And that produces a lot of energy, and then you pump it back up. The capacity in Europe is relatively limited. You would get through days and even weeks with the pumped hydro that we have in Europe, but not a lot more. If you want to get through the winter with the energy surplus of the summer, you will have to use some form of power to gas technology. So that will be hydrogen or synthetic natural gas or other forms of gas, as have been presented earlier on in the first presentation, which showed you the potential to further this in that presentation. In the first one that was showed, H2 was actually in the bottom left of the graphic, and there's lots of potential to therefore increase the energy density of the storage here. So the hydrogen system, as you can imagine, we will need lots of renewable energies. We can produce the hydrogen by electrolysis. We have to store it to deal with the variability of production and also the variability of consumption. We have to store it in various ways, as has just been presented, because we want to transport it, and that can be done in different manners. It can be put in a pipe, or it can be put into all manner of chemical solution and then transported by rail or by truck to all the points where it's necessary. And it can be used in all different manner of application. In industry, for example, you can use it to produce fertilizer. The steel industry is looking towards hydrogen to decarbonize, so to remove its coal needs and to replace them with gas and with hydrogen. In mobility, there is the possibility to use hydrogen, especially for heavy mobility. Indeed, if you're moving a bus around and you have to heat it in the winter or cool it in the summer, and then you have to go up a mountain, you'll find that the energy consumption is prohibitive, especially if you're trying to use a battery of electricity, and so you want to go towards a molecule. It could be used for heat. For heat, there are possibilities with hydrogen, there are possibilities with geothermal, and mainly it could be used for power supply. And actually, if you look towards the long-term scenarios of, for example, the German government, you will see that the favorite scenario is one of a very high level of electrification. And so the main role given to hydrogen in that system would be, as mentioned previously, to store the surplus amounts of power that we would have in the summer to be able to supply the energy system in the winter. It's also, I have to say, a more economic approach to trying to do it without. We can see that today in the sense that we have, for example, in Germany, a lot of renewable power in the north with wind, and we have some solar a bit everywhere, mainly in the south. But then we have a lot of wind in the north, and we're trying to bring it from north to south. And we have these rather annoying bottlenecks in the energy grid. And so what happens then? Well, we tell the windmills in the north to please cut themselves off. And then we ask, for example, a coal power plant in the south to start producing when it shouldn't have been producing. And so the net result is that we're paying for an energy that we're not using because we have to compensate the windmill for the fact that we're telling it that it can't sell its power. We're paying for the coal-based power that we're producing in the south. We're emitting CO2 that we shouldn't have been emitting. And so we have, all in all, a higher energy total system cost because we're paying for renewable power that we're not using. We're paying for coal to produce electricity instead, and we have CO2 in the system, which has a lot of externalities, as has already been observed. Should we be in a position, for example, in the north of Germany to produce hydrogen via electrolysis and to store it in en masse, we could then use it to produce power in power plants. We would not be producing CO2, and we would actually be putting the power from the windmills to use, and therefore the total system cost with direct and indirect costs would be much lower. So all in all, the storage of hydrogen allows you to reduce the total system cost. How much of this are we going to need? Well, we're going to need a lot of storage all in all. Why? Because hydrogen is probably not going to replace natural gas in a first step. So most of what we store is natural gas and oil, and we store it underground. And we're going to continue to use at least the natural gas for heat, and the first applications of hydrogen are going to go towards transportation and industry, and over time we're mainly going to use it to back up the power system. But in the coming 10 years, we're going to have to continue to store the natural gas that we have, and we're going to then have to develop hydrogen storage capacities. We have a lot of natural gas storage systems. On this graphic, these are the lines here in dark blue. These are the salt caverns, and here we have the total available storage. I'm showing the salt caverns separate from the rest of the system because, as you'll see later, they play a special role in the storage of hydrogen. The histogram shows you the needs to store hydrogen in the EU plus the UK. So this graphic is for the EU plus the UK in 2030 and in 2050. And as you can see, just the storage requirements that we already forecast that are coming already exceed the storage capacities that we have today. So we are going to have to develop more of these storages in the very near term. Methane and hydrogen, as I said, don't compete with each other, so that's why we're not going to start by just converting storages that we have today, but adding some. One of the tricky realities, as has already been explained in the previous presentations, is that the volume density of hydrogen is lower than, for example, that of methane by a factor of 1 to 4. And so the amount of volume of storage that we will need will certainly rise. And that also explains why it's very interesting to find storage technologies which allow us to save some space. So what are the technologies to store the hydrogen? On the right is what has been spoken about until now, so I won't go through it again. There is putting hydrogen in various chemical bonds. You can have hydrogen in itself, you can liquefy it, you can associate it with nitrogen or with carbon, and you can produce various molecules. You can put it in metallic hydrids, saline hydrids, as has just been presented. There are a number of solutions. But where do we put it? So on the left, you have a simplified picture to try and explain how we store natural gas today and oil, and where we intend to store hydrogen in the future. So you have a vertical cut of the ground. And so what did we do initially? We drilled for gas or oil. So we went down, say 1.5 kilometers, and we met various types of petroleum producing rock. They were generally tight, so the petroleum or the gas were not flowing out, they were contained, and we drilled through and we extracted the gas and the petroleum. And once these sources were empty, in some cases we were capable of reusing them to store, for example, natural gas. So the storage is tight. Generally the size is very, very large, but the speed of injection and extraction of the natural gas is rather slow. Then you have another technology. For example, at a similar depth, the white here is a salt formation. And so in some places, that's a geological given. For example, in northern Germany, you have it a lot. You have salt underground, and through tectonic movements, the salt has been pushed up into the shape of a dome. And so you can drill down, say again, 1.5 kilometers, and then you meet a salt dome. And then you can use water to flush the salt out. That will take a number of years, and you will have a large cavity. It can be, for example, 500,000 cubic meters. So you can put 2 or 3 skyscrapers in these cavities. And we have a large number of them in Europe and around the world today. And these salt cavities are the kind of technology that we store, for example, the strategic petroleum reserve in. So our 90 days of reserve of petroleum are in such salt cavities. So liquids can be stored in such cavities. And B, we store natural gas quite a lot in such cavities. And these cavities contain less, generally methane, than the porous rock, as shown on the left, but they're much faster to use. So the extraction and the injection go much quicker. And they are also very interesting in terms of storage of hydrogen, because hydrogen is today already stored in some places in salt domes, in cavities inside salt domes. This is done today in the UK in one site run by SABIC on the east coast of the UK on the North Sea. And B, it is also done in Texas. There are a number of salt caverns storing hydrogen today in Texas. It's always stored in gaseous form under pressure. But it's possible to store liquids that would not react with salt. It's possible also to store it in brine. So it's possible to store various types of molecules in various states, liquid or gaseous, in salt caverns. That is done today, and research is being done to see how we can either make new ones, for example, in Germany, or adapt old ones for later, for when we are not storing methane in them anymore. So the technology, it's known, it's being developed or adapted, and we will continue, of course, to see what we can do to store maybe other molecules than pure H2 or CH4. Now on a point of economics, and also linked to say, what do we want to store it for and what do we want to do? So here again, a graphic to show you different types of storage. So on the left, you have, for example, depleted gas fields, and here salt caverns. You can also drill your way through any hard and tight kind of rock. You can do the same and do it with ammonia. You can use liquid organic hydrogen carriers in tanks, or liquid hydrogen in tanks. And here there's the point on pressurized containers. So what is the point that I'm trying to make here? Here you have on the vertical an idea on cost, and here up here you have an idea of for how long you would want to store it for. So for example, if you want to store something for multiple years, you'd probably be interested in depleted gas fields. You'd probably cycle the gas in and out maybe once a year, and the cost in dollars per kilogram would be such. For salt caverns, as I mentioned, we can use them for the seasonal variability. We can store a surplus of energy in the salt cavern from the summer and take it out in the winter. And should we do that, we would have roughly this amount of cost as has been, say, researched. So if then you want to, for example, put it in a steel vessel and just pressurize it and put it in there, you can do that. But one has to consider that this is not for the same amount of cycles. So this is not putting it in the summer and taking it out in the winter. This is, for example, you're on a site where you're producing hydrogen continuously. You're filling a bottle and then you're taking the bottle away twice a day. So this is with a very, very high level of cycling. So you're talking about roughly 500 cycles a year. So this graphic gives you a rough view of what it would cost you to store your hydrogen, but it depends highly on the kind of use you want to make of it. And of course, for example, you could take a liquid organic hydrogen carrier, and instead of putting it in some vessel, you could put it in a salt cavern, and your economics would look very different from what they look like here. But this shows you a range from a minimum to, say, maybe a maximum of what the storage of hydrogen could mean in economic terms, depending on what technology you use and what application you want to do. And again, the most important point is that it depends really on the cycling that you're going to do. Is it going to be something that you're going to fill and empty twice a day? Is it something you put on the back of a truck? Or is it a huge salt cavern that you have and that you fill and that you empty maybe once, twice, 3 or 4 times a year? Moving on to what we're doing about it at ENGIE, given that we represent 10% of the storage market and that we tend to handle lots of natural gas. We have lots of projects. We have more than 70 in progress. They tend to be a very large scale. We're doing this in more than 10 countries. We have more than 200 people working on it, and we've actually been at it for 25 years. We have targets of producing 4 gigawatts at term, 600 megawatts by 2025. We want to build 700 kilometers of a hydrogen pipe, 170 by 2025. We want to store a terawatt hour, 300 by 2025. And of course, we want to also provide filling stations for people to use hydrogen transportation. Where are we doing this? As I said, more than 10 countries. We're doing it about all around the world. We have, for example, in South Africa, a project with some front loaders that do mining extraction. So these are very, very big vehicles, and instead of running on diesel, they could run on hydrogen. We are, for example, also producing hydrogen to produce fertilizer. We're doing this together with Yara, Project Yuri in Australia. This is a case where we would produce ammonia. We would put the ammonia on a ship, and we would take it then to Japan, Europe, or the Americas, depending on the market you wish to go to. We also have, of course, projects in Europe, plenty. We did the refueling of a hydrogen trail, a hydrogen train on rail, one that actually runs in the area of Hamburg. It was tested in the province of Groningen in the Netherlands, and we did the refueling for that train over there. We're also aiming at producing large amounts of hydrogen in the Netherlands with Project High Netherlands. This is to have a 1,000 megawatt production. And of course, we're also planning to produce hydrogen for transportation in various places. So that's for the mobility sector. For storage, I'm showing you here a map of Europe, and I'm showing you all the projects that have been recorded by Gas Infrastructure Europe last year. So not just our projects, but all those of the branch. And you can see in green, you have all the salt caverns generally concentrated in this area where the geology is favorable to salt caverns, also down the Rhone Valley in France and some in northern Spain. And projects based on salt caverns will probably be the first to come onto the market because, as I mentioned earlier, the technology is already in application in some parts of the world. And so this is the kind of technology that can be imagined as the first one to go towards for immediate projects. Then directly behind will be coming pore storage. Pore storage has, for example, already been tested in the underground sun storage project in Austria. A certain amount of hydrogen was put in there with a few quirks, interestingly enough, because of microbial activity down there, some of the hydrogen came back in the form of methane. So that's still at the level of research, but as far as safety was concerned, there were no issues. The project of Storengy I've highlighted. We have a number of projects in France, one in the UK, and one in Germany. The first project that we're aiming at and that we're developing and pushing forward is the project in France called HIPSTA. This was the first project to be funded by the European Union. It's a project that we are working on with various partners from various parts of Europe, some from within the EU and some from without. The first project is actually to test storing hydrogen in a cavern that was designed initially for methane, but it's a cavern that is not being used right now for methane. It's the first small one. It would be filled with brine, and then we will test pushing the hydrogen in, and we will test a high level of cycling of this cavern, and then we will draw conclusions, and we will share these conclusions with the public as the project is funded with public money. And when the project is successful, when we've determined the right parameters to operate it in, we will be going for the larger cavern, one that is more of a commercial size. This is a project that, as I mentioned, we are doing with a number of partners, and we aim at starting the testing this year. Construction works had already started last year. Interestingly enough, the project is, as many other storage projects, linked to a concept of production and consumption of hydrogen locally, of course, because the grids that will be required to transport hydrogen over large distances will probably only come at a later stage. So in the beginning, these projects are not started or planned in isolation from the rest of the world. They tend to be integrated into a first kind of a hydrogen project that foresees generally uses in mobility and the industry. So that's project HIPSTA. And we also have, for example, project Salty in the northwest of Germany. So what you can see on the right is a rough map of the north of Germany around the area of Hamburg. And what we expect there is to have a large surplus of renewable power with power grid bottlenecks going towards the south. So we expect it to be a very good place to transform this power into hydrogen. There are also LNG terminals that are being planned in a way that they are hydrogen ready, and mainly there is the pipe that is planned by Gasunie, the hyperlink that you can see here in green, and this pipe will go from the Netherlands to Denmark and passes via our site of Hazeveld, and so the project of Salty and the project of hyperlink are of course intertwined. So we believe, for example, that this is a good place, given that the geology allows it as well. This is a good place to develop further storages of hydrogen in various molecular forms and to store it in salt caverns in that area. How long does it take to realize such a project? That's also a point. If you're talking about a new project, it can take 7 years to actually get this project online. This is why these projects also have to be thought of and planned on the very long term. And of course, once we've made such a salt cavern, we are probably going to operate it for 50 years plus. So these are very long-term investments. And so that's why, of course, there is a need for a large amount of coordination with all players in the energy business, grid operators, storage operators, of course, also governments, and of course, this is all to be planned at a European level. So that was an overview of how we see the possibilities to store hydrogen underground in salt caverns, a view of how ENGIE intends to do it. Should you have any questions, feel free to ask.
Yes, thank you very much, Daniel. Thanks again to all speakers for that very interesting 3 presentations we have heard today. It was really great to get those insights from you as experts from the field. Yeah, I think we are already quite advanced in time, but nevertheless, let's try to have a short discussion round. maybe 2 or 3 questions. So I would like to start with a more general question. So today we have learned about various options for transporting and storing hydrogen. We have also seen that all of those options are particularly suitable for specific fields of application. Nevertheless, all options require dedicated infrastructures. Yeah, when we're speaking about pipelines, storage for gaseous hydrogen, importing of ammonia, importing of LOHCs, there we need dedicated infrastructures. And especially when we're talking about large-scale deployment, considerable effort must be paid to build those necessary infrastructures. And here my question would be, do you think that we can actually afford to operate several infrastructures in parallel, or will it then maybe better to focus on one system and to only operate one infrastructure? How do you see this?
I don't know to who exactly this question goes, but I think
to all of you. So yeah, I don't know. Maybe Daniel, we can start with you, then Volkan, and then Claudio.
I understand the need to find maybe the silver bullet or the magical solution. But generally, one size fits all doesn't really exist. It tends to end up by being one size fits nothing. And we operate various systems today: power, gas, oil in various kinds. And so I think that there will not be one winner. There will be various technologies supplying various needs.
Exactly. I couldn't agree more with what Daniel said. For example, we as well, of course, as you do as a company, always check what the competition does, what the market does. And we, for example, exactly know already as well that the hydrogen storage in salt caverns is by far, of course, the cheapest possibility to store hydrogen in that huge amounts currently, especially for seasonal storage. So I think you cannot go without that. But on the other hand, I think we've seen this already as well today, that even using that only would not reach all the hydrogen storage demand that we're actually looking for. So as we highlight already, I think in all of the 3 presentations, I think it's going to have, it has to be basically a mixture of all of them. And it would be a mistake, I think, to just focus on only one technology and only invest in that same infrastructure.
Yeah.
No, I cannot add much. Actually, you said everything, and that it's something that it's clear, and as it's clear that the most developed country, or the country that are rich in hydrocarbons, no, so like the country of the Arabic Gulf, so they will have the opportunity really to bring into the market a large-scale facility for storing hydrogen and transporting hydrogen. So that it will be necessary as a first step. Then, of course, countries that have less of a possibility will have to be assisted from a more developed country that have a good intent and not bad intent like in the past in finding the correct solution. So, but yeah, that is.
Great, thank you very much for your answers. Another question that popped up in the chat tackles the cost of storage and transportation. Maybe especially to you, Volkan, and Claudio. If you use carbonates or other LOHC materials for importing or storing large amounts of hydrogen, then you would need also a large amount of these materials in your system. How can LOHC-based systems still then be competitive with, for example, ammonia, where you don't need that amount of a carrier material? How do you see this? How do you think that challenge can be tackled?
Yeah. Again, I think I can start, Claudio. I don't know.
Yeah, absolutely. Go ahead.
It's as I said, actually, that we don't have to, we mustn't only focus on one parameter only for each technology, which I said was the energy density, for example. I highlighted as well, which is exactly the availability of each carrier. And the interesting thing is with the LOHCs, like that's what I said as well. The bigger the molecules get, the more difficult it becomes to really have them available in large quantities. Of course, this is a clear advantage of ammonia, of course. But on the other hand, I want as well address the advantage, or let's say at least highlight a positive aspect from our salt system as well, as we're using carbonate. And carbonates are like one of the most abundant salts existing on Earth. So there's, from our side at least, from the salt system, not a problem in availability at all. And transport cost is a different question. I don't know, but I can answer that as well, but maybe I just would like to hear from Claudia as well.
No, actually, you remarked correctly that it depends from, first of all, the quantity of material of hydrogen that we want to store, and also the distance at which we want to transfer the hydrogen, because then it will be a competition between liquid organic carrier and, for example, pipelines, transportation of hydrogen through pipelines, not to be forgotten, liquid hydrogen or ammonia. No, for larger distances, really larger distances, and large quantity of hydrogen, ammonia will play a major role. No, so that it's clear. No, but liquid organic carrier will play a big role in the smaller, for transportation for smaller distances. No, in all this, we have to insert also the possibility of storing hydrogen in metal hydrides. That plays a role. Technically, as the challenges are not so far from the one of liquid organic carriers. Fine, there it will be a matter of sustainability, because a large amount of metal will have to be found, no, and then that will be another issue. But the two questions is how much hydrogen and how far you want to transport, because then you can see that for really large storage, at a certain point, the salt cavern play a major role. No, so that when you cannot store large quantity or large volume of hydrogen, of material containing hydrogen on the surface, then you have to think that it's favored underground.
Great, thanks a lot. Maybe Volker, can you give us some more insights on how to produce the carbonates you need for your system? You mentioned that they are abundant in the world and they are highly available, but is it that you can just take like the carbonates from, I don't know, seawater, the salt brine, and then use them for your system, or is there a special treatment needed to produce the carbonates you need?
Yeah, I think we have to differentiate between several salts, I think. So first of all, I have to clarify that we unfortunately cannot use the salt brine from the seawater, which is sodium chloride. And I think this would be some kind of the holy grail if you could achieve storing hydrogen to salt water, where the same location where you already produce it from. So sodium chloride, I think if you would try to store hydrogen into it, remember that would be hydrogen chloride, which goes to hydrochloric acid. I think this is absolutely not a favorable step how we would like to store hydrogen. So there's like a huge amount of different salts, organic and inorganic salts, and carbonate salts are actually quite abundant. You find, I don't know whether you know, for example, stalactites and stalagmites. These are like super basic stuff that you find everywhere on Earth. And the difference between carbonate and bicarbonate, for example, is just actually a difference in the chemical equilibrium that you can shift easily just by adding CO2. So basically what we can do is we could produce our bicarbonate, for example, by capturing CO2, produce our bicarbonate and have even a negative CO2 footprint, which is quite interesting as well. Yeah, but unfortunately, we cannot use the sodium chloride from seawater.
All right.
I hope this answered the question.
Yeah, no, I think you answered it, and it sounds quite promising, even if you can't use the salt from the seawater. Maybe one last question to you, Daniel, which also popped up in the chat. Here, someone is asking, what is the reason why underground storage projects take so long to develop?
Right. So the say construction of a cavern requires you first to drill, and then to reach the salt dome. And then this salt must be basically flushed away with water. And this process takes a lot of time. So that's just for the realization. If you are to produce a cavern of commercial size, you will need to be doing that for around about 3 years. Before that, you've built your well pad, and before that, you've obtained a permit. Obtaining the permit can take 2 to 3 years, and I would say 2 years is pretty challenging. So you're looking at a minimum of 5 years, 5 to 7 years all in all, mainly due to, say, the process of creating the cavern, which can't be done very quickly. It's done by flushing the salt with water. That's the main reason.
All right, and how does those 5 to 7 years can be reduced when it's possible to use existing storage caverns for methane storage?
So I don't want to speculate as to how fast you could get a new permit, 1 to 2 years. And then you will probably have to change some equipments, because hydrogen is the smallest molecule that you can have. And so it will get into metals, it will get into cements, it will get into polymers, it will induce cracking in some materials. And so you will have to choose what elements you leave in, because you're confident they resist the hydrogen, and what elements you remove and change, because they can't resist the hydrogen, they could only resist methane. Generally, the closer you are to the surface, the more you're going to change your equipment. That's an observation from studies that have been done until now. So I think that those works could take roughly 1 to 2 years. So if you were to just convert existing caverns, you could say roughly around about 3 years. But as mentioned before, and as you can witness today, that the storage of methane is actually necessary where it is. So the tendency to take one of these and to put it into hydrogen, at least on the 8th of February 2023, that runs a bit counter to the objectives that we have right now.
Yeah, for sure. Important point. So I think since we are already 7 minutes past 8:30, let's conclude this, and thanks again for answering all those questions. Thanks again for your great presentations. I think we gained a lot of new knowledge today. And yeah, last but not least, I just want to announce that we meet next week, same place and same time, as Professor Kaltschmidt always says. Then we will talk about hydrogen transportation a bit more in detail, and there we will have presentations regarding the European hydrogen backbone, where the idea is to build hydrogen pipelines all over Europe, and another presentation about the technology advances in the field of liquid hydrogen transportation, which is another option I think we haven't discussed that much today. With this, I want to conclude today's webinar. Thanks again to all participants, to all speakers, to the team in the background, and have a good evening, and hopefully see you next week.
Thank you so much.
Thank you very much.
Thank you very much. Bye.
Goodbye, good evening.